my screen, one line by line. Okay, so you all can see the screen. Oh, yes, I'm sorry, I think that has gone away now. You can see the screen, right? And I'll just join my.
Yes.
Okay. Oh, okay. Let me just join my phone as well. So let's begin. Let me start in reverse chronological order. The first question was asked about question 6 in homework 5. So that's sort of I think the solution was a little bit terse. So I'll explain the whole thing in a second. I'll also explain the way I think about it. It might differ from what how Ishan thinks about it. That's okay as well. Let me just join this meeting on my phone. How do I do this now? You can see what you're seeing as well. Okay. Well, this nonsense goes on. So you start live streaming it, not yet? Okay. Yeah, I don't hear that. That's yeah, I'm not sure what's going on. Should I record it or not record, Ishan?
No, it's not yet streamed. I will ask them to stream.
Yeah, then I have to record. Let me know if I should record or not record it.
Yeah, I will check it. Then
And now it's live streaming it. I think it's live streaming it. Ishan, it's okay. Yeah. Okay. Just some time. So let's okay. Let me start now. So see in question number 6, let's review. Let me do it this way, so that hopefully the screen may be a little smaller, but I think hopefully it is. My handwriting is a little better this way. So the first thing someone asked was, okay, so let's go chronologically order the homework questions first. So in question number 6 in week 5, right? So okay, let me just rewrite the question first. So the model we assumed was that y was equal to x beta plus epsilon, and epsilon was normal 0 sigma square with a particular dimension. I'll leave the dimension out. And the matrix X was given by this sort of van der Waals matrix, which is 1, 1, 1, all the way to here. You have K plus L columns. And I'll just write it in my form so that it's easy to observe. So the first K1s were 1, 2 up to K. And the next, let's say, L1s were 1, 2 up to L. That's how the matrix looked like. This is 1, 1, all the way here, 1. And then on this side, the other part also looked like, just multiply this by k, 2k up to k squared, and then they had L, 2L up to L squared. Right? This is how the matrix looked like. Right? So this is what, and then you were asked to estimate. You were given. So let me write it in a general form, so that after that you guys can go and figure out how to do the specific question that came in the homework. And So whenever we give a matrix X and a linear model like this, the question becomes, write this in yellow, so the question becomes, sorry about that. So when so I take a vector P in R3, is P transpose B estimable? This is the classical question we have, right? And beta is a vector, P is a vector. So P is the P transpose means P is a 1 cross 3 vector, right? So or other way around, 3 cross 1 vector. Belongs to R3. So this is typically the question one to ask, right? So let's just backtrack a little bit, and then we'll come back to this question in a second. So I'll come back to the specific question in a second. So in this example, I think it was rigged in a certain way that the answer was obvious in the beginning, but sort of we were asked to do it in a step-by-step manner. So here's the, okay, so this is estimable. So let's say P transpose B is estimable if what happens? Let's go write it down line by line. So if there is a vector L in R3 again, vector L, I think, such that if I look at the expected value of L transpose the Y vector, so this is going to be equal to P transpose B. So if you can find an L, this happens, and then this is what the idea was, right? So you have this. Right. So now we know that that's the same as saying L transpose is Y is just the mean of this, the same as L transpose. That is, you find an L such that L transpose X beta is the same as P transpose beta. Right? So you have to find an L that this happens, because the mean of Y is just X transpose beta, X beta. So if you just backtrack a little bit, so L is so I should not call it L because LLD is there. Let's call this vector as, let's say, some vector, let's say Z. So X is a Z. This is an what do you call L plus K comma 1 vector, and the Z transpose is this Z. So now that is, if you can find a Z such that, I'll rewrite this such that X transpose Z is the same as P. Okay, so if I get this, I'm done. I can find given. So now it just, so here, so I know why it's not coming up. Let me make another one. So here, let me make it vertical so you can sort of see the nonsense. So let me explain the way I think about these problems. I don't know. So now the thing is that now I have to get P in the column space of X transpose. That's how I look at it, right? So then that's how I look at how to identify all vectors that are estimable in some sense. So then I go look at my X, right? If I go look at my X, this is 1, right? X transpose. X transpose is 1. So along the, let me write the first L columns in blue, so to keep consistency. So the first ones are 1, 1, 1, all the way 1, and that'll be accompanied by 1, 2, all the way up to K, and then K, 2K, up to K squared, right? And then these guys are going to be 1, 1, 1, up to 1, 1, 2, up to K, up to L, sorry, the L rows, or L column in X transpose, and then have L, 2L, all the way to L squared. This is what I have at X. So does everybody agree with me so far? This is what I get. You just see it on chat.
Yeah.
Or you can, yeah, good. Okay. So now once I do this, then I just try and see if I can quickly see. Typically in a linear model like this, you quickly try and see if you can find the rank of this matrix X transpose. So then what you do is you look at, ideally observe the first blue guys are all K, and these are all multiple K multiples of this guy, right? So So I can just kill this entire bottom first half and leave something here. That's okay. So what I do is I do, let's say I do a row operation. I do R3 goes to R3 minus, let's say, K times, my K is the blue guy, K times R2. So I do that. Okay. Then what I get? I get the same matrix. Let me copy this down. So if you're taking notes, you'll have a little hard problem because this iPad gives you all this funky ways of doing this. Let's do this. Right. So let me just move this a little bit. Sorry, okay. Well, then I have this. Then I've killed the first guy. I've made all this zero, right? By doing the operation. That's easy to see. This is all zeros, right? This is all zeros. And here I have a problem. Okay, here it won't become zero. So here, let me just write this a little bit differently. So let me write this a little differently. So the first guy will be 1, 1, 1, and then the bottom will be L minus K. The second will be 2 times L minus something. And okay, the first two rows remain the same. So that'll be dot, 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 1. Then this will be 2, and then dot, dot, all the way to L. And the last one will be L plus K into L minus, and then I have a blue here. I'll leave the blue. This is what I get, right? This is what I'll get as the row operations. So far, so good. I've done nothing fancy. I've just sort of eliminated one guy. Then I look at the second row. The second row, I can kill this person by just subtracting this person right here. This is one guy. And the same thing will happen here. And everywhere else, since both the things are the same, except the number is different, the operations will result in the same value. So what I'll get is, if I do R2 to R2 minus R1, right? So what will I get? I'll get here, this first row remains the same. We copy, I come back here, the same. And the second row, what will happen is, third row remains the same. I do nothing to the third row. Then I'll just copy this guy. That remains the same at the bottom. Paste it here. I'm sorry about the iPad jugglery. Easier for me to do it, but maybe hard for you to follow and write down. But if you do the computations at home, just keep doing it with me. It'll be useful. Then I get this guy. And then the middle guy, what happens? So this guy is going to be 0. Then this guy is going to be a 1. And I go till K minus 1 here. And similarly, here again, I get a 0. I get a 1. And I go till L minus 1. That's what I want to get. There's no doubling. Then what I do is I have a, let me make it in blue again. I have a 1 here at the top. I have 1 here at the top. Very good. And I have a 1 here at this guy. And then so on and so forth. Then I want to just I have only 3 rows, right? So I have 3 rows. So 3 rows. Then what I do is I try to sort of make this guy 0. So I get a basis vector here as well. If I do that, I get 2 basis vectors, right? So I go there. So I do a combination like R2, R1 goes to R1 minus R2. If I do that, that'll be quite okay. That's okay, I think. Then what do I get? So this here is where I'll do a little act of jugglery. So I'll just only keep my important rows, important columns. The first one is 1, 0, 0. The second one is 0, 1, 0, right? And then I'll just forget about this. I'll get something here, something here, something here. But these are all zeros at the bottom. They're all zeros. Last row 0. Last row I'll make in the same way. I'll keep track of it. Copy and keep track of this. And I don't want to keep all. I'll keep only my special ones. I want to keep track of it. Do expositions a little bit. I do all the way here. And then the last blue row will be something. Again, something, 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 and 0 here. 0 here, no problem. And then I go to the orange guy. The orange guy, again, this guy is going to remain the same because 1, 0, L minus K. That doesn't change much, right? And this person right here will now change to, again, 0, 1, and then a 2 times L minus K. Right? Nothing's going to happen here. I'm just going to leave it like that. Okay, L minus K here. And then I just forget the juggling. I just do something like, and I think even this I don't need. I just leave it as star, star, star. Okay, yeah, I just forget about these guys. I just put star, star, star. Here something happens, and I get star, star, star. Old fashioned. Okay, this is how the matrix will look like after I do this operation. Now I've just eliminated three possible columns that I'm interested in, and why? Now let's see. So the first observation is the following. So now, so the first observation is that, is this clear to all of you? The rank of X is at least 2. Is that clear to all of you? Because by the jugglery, I've been able to generate 2 linear independent columns of X transpose in R3. So I'll at least get a 2-dimensional subspace in R3. Right? Then the rest, I don't know what will happen, but these two will always help me get a 2-dimensional subspace always, right? It's at least 2. Then the other cool observation is that now, if this person was non-zero, suppose it's non-zero, then I could scale the last row by L minus K, and I could sweep out this guy, right? So here's the crucial observation. If the next observation is that if L is not equal to K, right? So not equal to K. If this happens, then if I do a 2 juggle, let's say I do R1 going to R3 by L minus K minus R1, and after that I do R3 going to R3 by L minus K. If I do both these row operations step by step, I'll just do it in one shot. What will I get? I'll get this matrix right here. Okay. And I'll use the same star for denoting a sort of an arbitrary number. So here what will happen? This will become a 1. This will become a 1. And this will become a 0. Right? And everything else will do something happens. So now if you notice, by this, if this factor happens, I've generated this guy and this guy as a 3 independent one. Then rank of X is always equal to. So, or rank of X, since I'm doing X transpose calculations, I'll just do X transpose always. Rank of X transpose is in rank of X transpose. So now this should now tell you how to solve the problem, right? Because now let me just do this let me just take this graph interval that I did. Let's see. So if we go sideways, let me show you the calculations. We can just check this together. So where was I? So I had to find a vector for which I had to find all possible P's for which X transpose Z equal to P exists, right? Now I found out, what did I do? I had to find. So then I proceeded to find, I want to find the rank of X transpose. So the way I did that was, I said, fine, I did row operations. I did some row operations. I just look at the matrix. I guessed these row operations, and no signs in it. And I found out I always have 2 linear independent vectors, right? And it's 3 the moment I have this guy. Now that's it. This should give you a hint of how to find your thing. I think the beta 1 is always estimable. This happens when L is not equal to K. So once this happens, any linear combination can be gotten. There's no problem. Otherwise, also you just try to see in any other matrix, any other vector that you have, you try to get to this. These 2 guys you can always get to quite easily by these two elementary row operations, and then see if you can guess a vector on that side, guess a vector L on that side. So this is an observation that moment L is not equal to K, any vector is estimable. Any is always estimable because this is always possible. Like moment rank is 3, so moment L not equal to K. But some vectors may be estimable even without L not equal to K. Right? So for that, the way you do is you just do a clever row operations to get to this idea. Right? So you take your let me just do the beta 1 case for example. So of course he has done go ahead. Any questions? Of course, sure. I'll mute you. Sorry. So here let's say you do the first one. Let's say to beta 1. That is beta 1 is the same as 100 times beta 1 beta 2, beta 3. That's what you want to estimate, right? So then all you do is you just take your X transpose, augment it with your P, and do a row reduction the same way. And then you'll find that do a row reduction to get to this form. So to get to this form, right? Get to this form. And of course, the last guy will change somewhat. The P will change to something else, right? So this is how the P will change. And then you can easily check if this is possible or not possible. I mean, you don't have to do this step. This step can not be. This step can be left as it is. It can be star, star, star. In this case, I think in the beta 1 case, this is enough. This is enough to do it. You don't have to worry about what happens to the orange part. Then you can immediately put your L vector, Z vector to put appropriate values of beta 1 and for the first row and the second row, and then everybody arbitrarily get the answer. And like that, you can do the other examples. Is this clear? Is the idea clear what I did? Everybody on chat? No.
Yes.
Yeah. So cool. So this is how I think just a way of thinking. I just think this way. I'm not sure how all of you think, but this is one way of trying it. Very cool.
The solution that's given though in that case would probably be not, because it says 2K should not be equal to L.
I think that may be a typo. I think Ishan will fix it. I point out Ishan today. I told him this week. He'll fix it. Ishan, have you fixed it already or not?
Yeah, I will fix it.
Yeah. So I think my calculation is correct, right? I don't think I made any algebra mistake. I don't think I did. I did just simple row operations and I got the answer, I think, right? I think it's okay.
I did it. I mean, I arrived at the same answer, but then I did a row reduction for X as opposed to X transpose. But I see this probably makes more sense. But I guess the rank of X transpose and X would be the same, right? If I did
exactly. You can do that yourself.
Right.
Yeah. Cool. But this is how I think about estimability, that you can always, this is how you can find this guy, you're done. That's what I think. Cool. Okay, good. This is one thing that's done. Then this I clarified. Very good. Then I want to do the next question that Kaushik asked, and then I want to do one R example, one with R, and I'll stop for the day. What time is it? 8:15. Is it okay till I go till 8:45? Is it okay if I answer this question?
Yeah, it's okay with me.
Yeah. Srivinay, Prashant, and Utkarsh, is it okay with you guys?
Yes, it's okay.
Yeah. Okay. Thank you. Okay. Let me just let me just finish it. Okay. So the next question that was asked was that how do I show the sum of squares is independent of this other one, right? This is what was asked, right? So let me just go through that. Just finish that proof for a second. That's just sort of a. It's not like a. It's a trick with normal random variables. So let me just tell you that how to do that. So let me write this down. So again, this question 1, right, Kaushik? I'm not sure. I think question 1.
That's right.
Question
number 1.
Right. So I think the SSW, right, was how does one? Okay, I'll write it my way, then Prashant can see how to do this. So Ishan can see how to do it. So summation over I, and then I have I equal to 1 to M, and summation. This may not be the correct notation used in the quiz, but I'll write it this way. Okay, so Yij minus Y. Just tell me if I'm wrong. I think this is correct, right? This is the sum of squares within groups. That's correct. Okay. And SSB is what I think is the mean guys, right? So SSB will be all the mean guys. So SSB will be, I can think of it as the sum of n and times the sum. I'll just go between the groups. This is m groups. And then I'll have a yi bar minus y dot bar minus the whole mean, that is y dot bar whole square. This notation is correct. Do you agree with me so far?
Yes.
Oh, very good. So now I have to show these two people are independent, right? That's what I show. Right? So the trick is not the trick. The sort of the knowledge required is a probability exercise, which I'll write it down. So I will not prove this, but this we can verify. Easily. I don't think it's a problem. It's a probability exercise. That's where this is based out of. So maybe the solution is a little cryptic. I looked at it this morning, but that's okay. I think it's there. The exercise is the following. See, suppose I take n independent normals. Okay, so I take x1, x2, xn, or let's say IID normal, not independent, IID normals, or IID normal random variables. They don't need to be standardized. They're just normal random variables. But they all have the same mean and the same variance. So they're IID. I take this guy. Then we know that x bar also is random. X bar also is a normal random variable. This we know for sure. And then you can check. This is the exercise. This is the standard. This is to a standard. And the exercise is that x bar and these two guys are independent. So I'll tell you. I'll write the vector down. x1 minus x bar, x2 minus x bar, and xn minus x bar are independent. This implies this. So maybe here I'll just remove the fact that it's normal that you can check as an exercise, but that's not one. I don't need that fact for this. I'll tell you in a second. X1, xn is equal to x bar is equal to 1 over n, summation I equal to 1 to n xi imply this. So can someone just say how would one approach this exercise if you were given this? The x bar and each of these guys are independent. How do you show this? The collection independent. How do you show that? Do you know? Intuitively, do you see it immediately or no?
I don't.
Okay, so let's look at a simple one. If I want to show x bar and this first guy are independent, how would I do it? You know how to do it. Suppose I give you two random variables like this. How would I show independent?
Just correct me. So my theoretical understanding of this is just to test for independence. The product of the expectations are 0 or something. I mean, that's
exactly. So the thing is that you can for normal case that's enough to verify. Uncorrelatedness is the same as being independent for normal, right?
Right.
So you just have to verify that these are uncorrelated, and that's just a computation. So this is you can do it just take the mean of this and take the mean of these guys and then show that the mean vanishes. The product of means is mean of the products. Therefore,
the product of the expectations will be 0, right?
No, EXY is EX times EY. You can show this in this case. Take an example.
Right.
That's
right.
what I was showing. So,
correct. Oh.
That's what I was show. That's the exercise for this. So once you have this observation, then I think the rest of the proof is sort of you can do it for standard normal because our you can do it for a normal 0, 1 and see if the proof works. Then everything is 0, no problem. EXY is 0, it's just short. So once you know this fact, then the problem becomes quite easy, and it's not a problem. Then what you do is you observe the following. So you look at you fix for each I, you fix an I. You fix an I, fix I equal to 1 up to some fix an I. Right? Then you look at yi dot bar. Right? That comes from a mean of normal random variables. So that's independent of this guy, right? Of the other guys. yi1 minus yi dot bar, right? All the way up to yin minus yi dot bar. Like using the exercise, using the probability factor. The fact you fix for every fixed I, this is true, right? Is independent. That's the first thing. But then you observe you go back to this person right here. Let me bring this down one page. So let me make everything one page so it's easier for you. I'll cut it again. Let me just leave this here. I'll copy this and bring it down again. Okay, so I've used different y's and different make this all same y. So in same style. So don't confuse again. So this is yi dot is yi1 minus this, and then little y and little y. Right? Then I go and observe this two right here. This guy right here. I paste this, right? So what is this? This, let me go observe slow. This SW is a function of what all? So it's a sum of all these guys, right? Of all yij minus yi dot bar. That's for I equal to 1 to n. It's a function of these guys. A function of this, I equal to 1 to n. It's some function of these guys. Each of these people. So which is like of this phenomenon right here, right? On the right hand side. Right? And this person right here is a function of all the y dot bars, right? So yi dot bars, right? I equal to 1. And here I've shown you that for every fixed I, this is true. And this is an independent function. Let me put this here. Let me make this all one color. Pink is one color, and this all yellow perhaps. Is yellow perhaps. So then there's a standard probability interpretation that if one random variable is a function of only one set of people, and they are independent of the yellow guys, and the other guy is a function of only those yellow guys, then this implies that they're independent. That's just a probability factor again. That this implies that SSBs. We just open these two windows and show you the proof. So it sort of it came one page. So I don't know how to do this 2 pages. Oh, it doesn't come out. Sorry. Good. Very good. So is this idea clear? This is what I'm doing. This is the
Yes.
So it's just a jugglery of probability facts that we have. See, also like in linear models, right? The moment you assume this Gauss marker, whatever this normal random variables, then you have tremendous amount of tools at your disposal to play with. And always go back. If you can't show something, just go back to, okay, what do you know about normal random variables? And then you come back and work forward. Because once you know the probability exercise, everything else is sort of what do you call sort of an act of sort of stomaching the notation. There's nothing else going on. So always don't get scared by the notation. Linear models, you have all these sums, blah, blah, but everybody is a normal random variable. And if the I and J's don't intersect, the independent comes automatically. If the I's intersect also, then something funky happens like here, and that's how you go.
And maybe a super question. So there is covariance of these two. If they are 0, doesn't mean they are independent.
That's right. So that's only for normal. Only if they individually, here there's squares, right? So the distributions are normal. So
right.
So only if two random variables are normal is the covariance, and the covariance being 0 is same as independence.
Right. Okay, because these are chi-square distributions.
Exactly. That's not true. That is not true.
Okay.
The independence is equal to covariance being 0 is only for normal random.
Only for normal.
If you haven't done, if you want a small refresher in this, let me know. Like confidence intervals testing and the normality, I can do one class on this. Just ping me on chat and we can do it once, like a special class outside these sessions.
Sure, I will.
Yeah. Like just basic probability calculations like this. If you want a quick sort of summary one day, we can do it.
Sure. Okay. That like to refresh.
Yeah. Okay, so I'll take a 2-minute break. I'll use it as 2 minutes, come back, and then we'll do I just want to go through an R example so that all of us are on the same page after that. We'll close for the day. That'll be complete the review for the 1 to 8.
Sure.
Yeah, give me a second. I'll just come in 2 minutes. I'll leave this on. I'll just mute myself. So I've just sent an R script on the Zoom chat. And then you can sort of just, if you have R Studio, can you just open R Studio and load up this code, and then we can sort of start from there. And I'll try and see if I can do. You can see both the screens in a second. See if that's possible. I want to write as well as sort of show you this. See if it works.
Have we sent the code already? I'm not able to.
Yeah, on the I didn't send everybody. That's why I did it. Sorry about that. I'll just do it everybody in a second. I thought I did it just now, but it didn't work. What happened now? Oh, I don't know. So now. Right now it should come to everybody. Can you just check if you guys got it?
Yes.
Yeah. Okay. So let's just do a simple competition, and so we'll just close the class with that. I just want to say. Let me just do a small adjustment to my screen on my computer. I think some of you may know how to do this, but I just want to make sure that no plotting. I can do this. Right. Let me come down here. Let me share screen. See if it works. Give me 1 second. Just close everything. I'm able to get this. Let me see if it works. Okay, can you guys see my screen or no? No, you can't see both, right? You can only see the. Interesting. You cannot see both this screen, right? Some reason.
Yeah, I'm seeing only the iPad screen, the notes.
Yeah, notes, right? Why is it not coming? I don't know. Okay, maybe the notes. I have to flip. Let me just do it separately, and I do the flip, and I do it each one separately. Okay, so the template is here, and this very good. Okay, let me share desktop again. Let me see if that works. And then let's see if it works. Okay, so now you're seeing my iPad. Yep.
Yes.
And now you're seeing my R Studio, right?
Yes.
Okay, I'm not able to show both of it together, but we'll take it like that. We'll see how it goes. Okay. So now I just want to do this simple thing. I just want to just do a simple. I mean, it's like a review, so I don't sort of. It's not meant to be something that's crucial for the reviews or what I just wanted to. So what I want to do was I just wanted to go back to this review the following. So this is in Faraway's book. I took it from there. A data set called Gala. So you need Faraway's package. So this is called library Faraway. You need it. So if you have not installed it, can you take a minute to install it and let me know in chat if you installed it or not? This is a good package to install per se. So Prashant and Kurt, let me know if you installed it.
Yeah, I have.
Prashant? You're the only two brave ones.
Actually, I'm unable to get the R file. So maybe
you have not got it yet, or you have got it yet?
I downloaded it, but it's not opening in my phone, or I could not share it to my laptop. Maybe I should join with laptop and download it again.
Okay, so should I just carry on with the lecture, or you want me to wait?
So you can carry on. Yeah.
You sure? Okay, but you have the code with you, right? You keep the code, okay? Okay. So what I want to do is the following. So this is like Faraway has this what do you call this thing? Okay. So Faraway has this data set called Gala. It's a Galapagos Island data set. So what they do is they want to understand what are amount of species in the island, So let's go and load the data, library far away. Let's go data. And let me go and check what data looks like. Let's do head of Gala. So what it does is it in each of these islands, it's off, I think, Santa Cruz in the US. It counts the number of species and then how many of them are endemic, area, elevation, which nearest to this, and then screws and adjacent. And that's what it does. I think you can just check what Gala. You can just check later on what Gala exactly is. You can check it now quickly. It's not coming from me because I close that help window. Okay, so my help window is closed here, so I won't. This you can check it will come. Yeah. So now what I want to do was I wanted to see if let me go to my iPad here. Let's click on player. So I wanted to see if species had an effect on area. If this is true, species can be given as a linear function of area and elevation. So I just want to just check if these two parameters mattered in my as a linear model. Can I fit it like this? Right. So beta naught plus beta 1 plus beta 2 plus an error. This is an error I model again by normal, and I just want to check if this thing is true. Okay. So this is what I want to check. Right. Let's see. I want to check. So now I go here. So the first thing I do is R has an inbuilt function. So let's go inbuilt linear model function. Model function. So this Kaushik, I don't have it in my code. You have to type it yourself. Huh? Let me know if you're able to type it along with me. Should make it a little bigger, maybe. I'm not sure. Yeah.
Sure.
Yeah, make it bigger.
I'm okay.
Yeah. So once you do that, you're here, right? So now you're here. Now let's run this code. I do models. So if I go to model, and then I do model summary, let's say I do summary of models. I call it model S. So now I go down and I type in the console model S. Okay. So then if I enter, it'll give me a bunch of things. So let's just try and understand this output. It does this homework. So here it tells you, right? The formula is I want to get species as a function of area and elevation, and the data set is Gala. That's what it says here, right? And then this is the residuals, how the residuals behave after the estimation, the minimum, the first quartile, the median, third quartile, maximum. And these are coefficients, right? So let me just go write the coefficients down. So what it's telling you is that, so maybe I go to my iPad now. So here the iPad is, this is beta.
Sorry to interrupt. Just a quick question. See, the residual summary that it gives, right? That gives you the min, max, and all that.
Yeah.
Is that because it's trying out different models quite physically? I mean, like what we did in our assignment where we drew 100 different models and we chose the best out of it.
Let's do this. Very good. Let's check that question. Now let's look at the number of rows in my Gala. Okay. So there are about 30 rows, right? So it should give you 30 beta. The residuals is 30 of them, right? So why not minus beta 1? So what is the residual? Residual I.
Oh, okay.
That's all, right. So here I have. So let me go and copy it down. Beta 1 hat would be something. Beta 2 hat would be something. Beta 3 hat would be something. Let's just go and check what the model gives you. So model gave you 17.10519. That's beta 1 hat. Beta 2 hat is 0.018, right? And beta 3 hat is 0.17174, right? This is what I have, right? This is what I got from the R. Is the idea clear? This is what I got. So
can you please send the R file again?
You want R file again? Okay. Are you on a computer right now? Okay, let's do it. Sorry, I didn't check the chat. I'm very sorry. Thank you for asking. So we're on the way? Yeah. You got it now? Oh no, I didn't send it to you again. Oh no, I didn't get sent you again. What's going on? Why is it going to Ishan all the time? I have no idea. Yeah, now it should. Does it come to you again? No, you got it?
Yeah, I got it.
Okay, thank you. I'll go. So now we have this, right? So now the residual I, so So there are 30 points. So this is this thing. Now we have 30 points. So we have 30 data sets, right? So this is the thing we have. Then we have 30 data sets, 30 data points, right? Then the residual I would be just yi, which is species, minus this whole thing, right? Minus the beta 1 thing plus. So Kaushik, does this answer your question now? That's about that thing?
Yes.
So it's just plotting how the thing looks like on that line. Very good. This is what we have. So that's the residuals. So it's giving you some residuals right here. Then these are coefficients that you have. This is standard error of each guy, of each of the beta ads, right? So it's like we'll come to this in a second, how to get this done, how to find errors, and this is what is happening. So what R is doing is in this LM function, this is our LM function. Let me call it our LM function. So this is what R would do, right? So if you did not know any statistics, you didn't come to a class, you just went. But now you know in class, you know that to get the normal equations, you just have to solve X transpose X beta hat is equal to X transpose Y, right? Where X is the appropriate vector that you have there, right? It's 1, 1, 1, and so on. So now what I did was I in this code, let me come back up, let me come back down. I could probably go to the top now. Let me go down. A little bit smaller. I have to stop sharing. Let's try share again. Give me a second. My R is acting up. Studio acting up right now. Sorry about that. Very good. Oh, very good. Sorry. Okay, I'm back to sharing screen again. Cool. You guys see it now again? I'm sorry. Yeah.
Yes.
So what I did was, now this is what R did, right? So now let's do it by hand. Let's do the whole thing by hand. Let's do it by hand. Let's try to find the beta hat by hand, right? By hand. By hand mean by hand R code. I should just call it the down. So what it was, first I made this X as a matrix of I made the X matrix. Let's go. What's happened now? Where's it coming? I have to start again. Go here. X is this. So let's go look at X. So X is this matrix that we have, right? All the area numbers are there, and the element numbers are there, and the one number is there. That's the X matrix that we have. And then that's my X that I already have from the data set. The intercept is all 1, 1, and this is the X matrix. Then I go and put the Y value. That's a species 1. That's the Y. So if you go down here and I do the Y, that's all the species data that I have. Right? So this is what I do, right? So is this idea clear? I just so in my
yes.
Okay, so let me just do this. So what I do is I do my X is just this 1s and this A1 up to A30, and then this is just elevation 1 up to elevation 30. And my Y vector is just Y1 is species 1 up to species 30. Correct? That's what I'm doing. There's nothing else I'm doing. And that thing suddenly becomes really bad on the horizontal line. Sorry about that. Okay. Try to fix this when I upload to the website, perhaps. Okay, very good. So this is what I did. So are we back on the on the R now? Very good. So then I do this. I just get X transpose X, which is TX is transpose of X times X, right? That's what I do. X transpose X. That's XTX. And then if I just do XTXI, it'll just be a matrix of this form. Just a 3 by 3 matrix. That's what I get. Exactly what I get. So that's what X transpose X is. So let me just call it as let me just write down. This is just doing X transpose X. Right. And then here I'm solving for beta hat, right?
how 1 1 come at the first column? Like in line number 7, you have
1 1, right? Yeah, that's because that's just, you need that
R code in the R code.
in the R
Okay,
code.
in line number
Yeah, that's just tilde will give it to you. That's
Yeah, tilde, okay.
That
Okay.
product will give it to you. This is the package in Faraday does it for you. You can do it by hand also. The package in Faraday does it for you. I'm using Faraday's code, so I'm not using my code, just to sort of be clear. Let me just should write it down to you. So beta hat, if I do, then if I type beta hat, I should get exactly what I got from my linear model function. Let's just check that. The beta hat was this, and I type in, let me go type model again, model S again. And you see the same beta hat, what I got here, 17, 0, blah, blah, the same as what this guy got here, right? So our R is doing the same thing, not doing fancy. Is that clear for both of you?
Yeah.
Yes.
Yeah, this is what it is. Now, this is not needed, names model. Okay, we can do names model and names model S also. So if we do names model S, the data frame has all these things, right? It's called call, terms, residuals, coefficients, alias, sigma, df. You can use this as well, okay, to capture the various statistics that come here in this table. So if you want the F statistic, if you want the thing like that, it'll come. It'll even give you the covariance unscaled and so on. And R squared as well. It comes right there. But let's do it by hand again. So this is so names model S. Okay. So what you can do is, let me move this up. Okay, let me leave it here. No problem. Let me just say that you can use LMR to get all the information on testing. So let's go and look at this thing. What is the model summary gives you? That's what I did here. So first it gave you the first column is, this column is just the, let me just annotate to be easy first. Think about it. Okay, I can't annotate on the screen, I guess. The first column gives you the coefficients, right? 17 blah. The second column, what it give you? It gives you the standard error for each of these guys, right? So let me go down, right? Let me go down and in my iPad, you can't see it right now. Give me a second. So second column gives you standard error of this standard error of beta 1 hat is, it tells you it is going to be equal to 20.94, right? 20.94.
Oh, we're not seeing your iPad.
No, I know. I'm just reading off the R screen first.
Oh, okay.
Then I'll show the iPad in a second. So standard error of beta 2 hat is, or you can read off for me. I'll write here. What's the beta hat 2 hat is what? From the R thing, can you read off? Okay, one of you read off the standard error for beta 2 hat in the second column of the model S. Let me go back. So standard error is 0.025 and 0.053. You guys got that or no? Is it clear or no?
Yeah, 0.02594 and 0.025.
Okay, that's the third, right? And the last one is giving you the t-test value, t-test prop, t-test. There is the probability that the t-statistic, I'll tell you what the t-statistic is, as ti is bigger than whatever we observe here. This t-statistic, let's call this observation as, I think it's just beta I hat by standard error of beta I hat in absolute value. That's what's said. That's what the last one's giving. Last column. Okay. Those probability. So and then what's happening is that it's doing a 0.05 level of significance. So this elevation is not sort of not significant. There's sort of that if you do individually, if you test for elevation and area, the elevation seems to be not significant at all. That's what this line is saying. This 0.03 value is saying. Okay, so let me write it down the thing. So so one conclusion is that the p-value, okay, for beta 3 hat alone, if you do individual testing, this is like this is less than 0.05. So you'll reject or not, you'll sort of so you have evidence to sort of it's not significant. So that means beta 3 could be 0. It's not really there's no evidence to reject null hypothesis. The null hypothesis in this case was 1. This case was each of the beta I is equal to 0. So that's what happens. You're doing individual testing, huh? You're not doing combined testing. Okay. That's the t-test, right? That's what the t-test is. You test individually for each of the factors. Right? Very good. Then the other thing that we discussed was how do the f-test. The f-test is the one that that tests this following hypothesis, right? This is the f-test is the one that tests in one shot. Beta 1 is equal to beta 2 is equal to beta 3 is equal to 0. And the alternative is that the null is not true. Right? No null. Right. That's what the f-test does. So you go look at the f-test variables in the data set. In the R, so not data set, in the R code, what do you find? You find that the f-test tells you that it's 16.7 on f has two parameters, is n minus the beta 1, beta 2, beta 3 has 3 minus 1 is 2, and 30 minus 3 is 27. That's the, and the p-value is very, very small. So you reject the null hypothesis. That means, so p-value is very, very small. Is very, very small. So you reject the null hypothesis that this null, you reject the null. That means all these factors are important put together. In this case, you get only only you get the third one is significant. The second and the first are not significant. I think I said the reverse before. I'm sorry about that. But if you do the f-test as everything together, then the p-value is very, very small. So it's okay. Very good. So now I do a residual standard error that's 79.3, and then the multiple R squared statistic was this, and adjusted one I won't think about. I haven't discussed in class. I'll forget about. Okay. Now let's just do all this by hand. Okay, let's do all this by hand. So let's do all this by hand. So now, if you want to do it by hand, you look at I'll go back again. Let's use everything. Let's do testing by hand. By hand code and all. Right? So you all get an idea of what's going on. So first thing is I have to estimate the variance, right? The variance. So sigma hat is going to be, the variance is going to be what? Sigma hat, we discussed in class in the notes that sigma hat was just going to be equal to the sum, the square root, right, of the residual sum of squares by n minus, in this case, n minus 3. That's 30 minus 3, right? Which is what I have there. So, and the residual sum of squares, we know exactly what it is, right? It's just these. I took the residues from the model and I get this result. So that was sigma hat. So let's see what that gives me. Sigma hat is this, and sigma hat was giving me 79.36. That's what it gives me. So quite cool. Let's keep that in mind. 79.3368. Let's keep that in mind. Then the standard error beta hat is what? The standard error beta hat, this we know, somebody asked me in the homework as well, how to estimate the variance of beta hat. Standard error is just this. It's a square root, right, of the diagonal elements of X transpose X, right? And you multiply that by sigma hat that you have. To do that, you have the standard error of each of the beta hat. Let's just check that. What do you get? I get this, I get this. So here I got 20.02 and 0.053. That's the same as what R gave me. 20.94, this thing and this thing. Yeah, that's the form. Cool. This one. So is this idea clear? This is what R is doing, right? So estimating the standard error beta hat. So R gives me the answer. This is a vector. It's a 3 vector. Can someone read out the values now for me? Kaushik or Prashant?
Oh, yeah, I'll have to run it just.
Yeah.
Which value?
The sigma, the standard error beta hat.
Okay.
It's 20.942 for beta naught.
Yeah, and then
0.0259 for area, and that is beta 1, I think, and then 0.053 for elevation. 0.05. Yeah.
I got right. It's 0.
Only
1 0. Only
yeah,
1
0. In both. Yeah, even for 0.
Thank you. So this is what you get. Very good. This is what I did by hand. Right. So it matches the R thing. Right. Very good. So then I want to R square statistic, which is just again 1 minus this thing. Let's just check what R square looks like, and do the same thing. R squared. This is 0.5 exactly. So R squared was what? R squared, like we discussed in class, is again going to be equal to. So it's 1 minus the sum of the residual sum of squares. So 1 minus real sum of squares divided by the sum of the means, right? The summation I equal to 1 to n of yi minus y bar the whole square. And this came out to be 0.5. This is what I have here, right? It's quite cool. So far we are good. We have gotten all the whatever R is computed, at least in the parameters here by hand. Right? Okay.
Yeah.
Okay, very good. So R also gave the little standard error sigma hat is 79.34. We got 79.36. Very cool. So now I have to get this TSS and RSS. Let me just finish that and then we can stop for the day. So the total sum of squares is again since I won't write it down, total sum of squares, and this RSS is this. Let's go TSS RSS. This we already done before, so TSS is going to be this much and RSS is going to be this much. This we did. All right, so TSS we know is exactly going to be equal to the total sum of squares. That is just sum over each of the species I equal to 1 to n, yi minus y bar. The whole squared, and RSS we know exactly what it is. RSS is just sum of the residuals is just summation I equal to 1 to n yi minus beta naught. Sorry. Oh, I'm not seeing the iPad. Let me go iPad. Yi minus beta 1 xi minus beta. Sorry, beta 1 is alone. Sorry about that. Beta 1 minus beta 2 minus beta 3 minus x1, so no x1. I'll leave it in yellow. I'll leave it in orange. Okay. Leave it in yellow. X1, x2, or x2. Okay, I'll just call it x2, x3. This is what I have. It's the residue sums. So this is the TSS and RSS, and we know this should be the T statistics is this one. We'll come back to that one. Let me not put this. This is not the right one. I think I made a mistake. Yeah, T statistics is somewhere else. Okay. So here I have to do this F statistic. So F statistic, I can get the degree of freedom from the model. I know it's 27. I can do that. The F statistics is just TSS minus RSS whole squared by RSS by this one. That's the T statistic. And if I do this, and I get that 1 minus p value is this, and that's the same p value that I got in the RS. And the T statistic is just beta hat by SE hat. If I do the T and the two thing, I get exactly what this also got. The T statistic. P value. Cool. Let me write this down. So then you can compute the F statistic. So on the T statistic as just T statistics for each parameter. So for each I is just beta I hat by SE of beta I hat. And you do the T test on that. And the F statistic is just like look at right here, it's just TSS minus RSS whole squared divided by, so the total sum of squares minus RSS and the whole square, right? Divided by 2. This is the degrees of freedom of the p minus 1, and then the whole thing divided by the thing that you have at the bottom. RSS by n minus 1. You'll have RSS by 27. So you can perform the F test and the T test. Yes. Yeah, sorry about that. I think I've gone well over time. I need to do that. I hope this was useful for all of you to do.
Yes.
Yeah.
Just
So
a quick question. That standard error for the individual
right.
For betas, right?
Yeah.
So that comes from where? Because we learned standard error for the whole thing, where you said square root of RSS by the degrees by n minus 2 or n minus 3. That's the standard error for the.
Yeah, so standard error the same way. You know beta hat is X transpose X inverse X transpose Y, right?
Right.
Then you do the error of that is standard error of that side is the error of that side, right? And then you use the same answer you get.
Oh.
The covariance on that side, you put covariance sigma squared on that side you get, and then sigma squared is sigma hat squared, and get the same thing. Do you see what I'm saying?
Yeah.
Just give it that. There is no problem. You just use the fact that beta hat is X transpose X inverse X transpose Y, and then the variance means you just do normal variance computation, you get the answer.
Right.
Is that clear? The idea is clear?
Yes.
Okay. I'm sorry I went really over time. I didn't mean to do this. But yeah. So I'll post the R code and the PDF file on Slack, and Ishan can post on the website as well, and on the discussion forum on the IT Madras site.
Sure. Yeah. Thank you.
Okay. Thank you. I'm sorry I just went over time.
Thank you so much.
Yeah. I hope this sort of gave you a review of the whole course, and then it's gonna give it until now, till week 1, till week 8.
Yes. Let's put everything in context for us.
Yeah. Okay. And then when you come back next week, we'll start doing ANOVA and all that in an applied context and work with that.
Sure.
Okay.
Thank you.
Thank you. Bye-bye. Ishan, I'll leave the meeting. Huh? Thank you.
Yeah, thank you, Siva. Bye.